What's up guys, it's Sean here from The Computer Scientist. Today we'll be evolving our hill climbing agent from last video to use a deep Q network to solve OpenAI Gym's CartPole environment. A deep Q network is essentially using a deep neural network to model the Q learning function for reinforcement learning. So recall that the typical reinforcement learning problem involves an agent interacting with an environment with the goal of selecting actions that will maximize its long-term reward from each episode of interaction with the environment. It starts where the agent in an environment is presented with an initial state and has to select an action to take in the environment for the current time step. Then the environment responds with a certain reward value, a resulting next state, and whether or not the episode ended. So then the idea of Q learning is for the agent to eventually learn a function that uses the state for calculating the expected long-term returns of taking each possible action in a given state, which it can then use to select the action with the highest return. But since the reward behavior of the environment is initially unknown, the agent needs to explore the environment's rewards from taking different actions in various states in order to build up this function. Now, there is an equation that models the expected long-term reward of taking an action in a particular state, and it is given as Q of the state and action equals the currently observed reward plus the discount rate gamma times the maximum of the Q values of the next state. This is called the Bellman equation, and I also have a video explaining how it's derived in case you're interested. So for modeling this function with a neural network, we need to approximate two outputs. One is the vector of Q values for each action in a given state, and the other is the individual Q value for a single action in that state's vector. So to build our network architecture, we start with the state vector, which we will pass through a dense layer, acting as the hidden layer with a certain number of hidden nodes. Then we can pass that layer to another dense layer to transform it to have an output length to match the number of actions available. This will be our vector of Q values for the input state. Then for the Q value for a single input action, we just want the value at the index corresponding to that action, which we can get by multiplying this vector with a one-hot encoded action vector, which has a 1 in the index of the action and 0 elsewhere. Then we take the sum to get a single value. So now with our target value calculated from the Bellman equation, we can calculate the mean squared error of the network's output with the target to get our loss. So now that we have our neural network architecture, let's code it up. So I'm back in our Jupyter notebook from the hill climbing tutorial video. Since we'll be using Tensorflow for our neural network, we need to import it, and we'll also print out the versions of Gym and Tensorflow for reference. If you're not too familiar with Tensorflow, I have an intro video on the Tensorflow Basics, which I'll link in the description. Then we will start by renaming this hill climbing agent class to DQN agent, and we don't need the old build model and update model anymore. This is because we'll create a new class for our neural network model, which takes in the state dimension as the network's input size and the action size as the network's output size. So we'll first create our state placeholder as a float, with the first dimension being none for any batch size, and then the rest of the dimensions coming from the values in state dim, which we unpack using the star operator. Then our action placeholder will be an integer for the action index and having a shape of just the batch size. Finally, our target placeholder will be a float, just having the length of the batch size. We also need to convert our action index placeholder to a one-hot encoded vector by passing it to TensorFlow's tf.onehot and specifying the depth as the number of actions. Then we get our hidden layer by passing in the state to a dense layer with 100 hidden units and with the ReLU activation function. We then get the Q values for each action in the state by passing this to another dense layer, outputting action size units. Then our single Q value for a state action pair comes from multiplying the state's Q values with the one-hot action vector, and then reducing this to a single value by summing across the columns. Then our loss is the squared difference between the predicted Q state action and the Q target, which we will average out over the batch. And for our optimizer, we will use the Atom optimizer, set the learning rate, and pass in the loss to minimize. So now that we've defined our network graph, let's see how our agent class can use it. So we can start by creating an instance of our Q network, passing in the state dimension and the action size. Then we need to update our getAction function to return an action for the given state using the Q network. So the agent needs to select the action with the highest predicted Q value, so we need a way to get the output Q state vector from our input state. We therefore need a TensorFlow session for running inputs through our graph, so I'll create one in the constructor and also run the global variables initializer, which will initialize the weights and biases of our dense layers. And whenever we open a TensorFlow session, we need to remember to close it when we're done, which we can do in the destructor. Also remember that the global variables initializer should be run after the graph operations have been defined, otherwise there won't be anything to initialize. So now we will define a function in the QNetwork class to get the QState output, which takes in a TensorFlow session and the input state, and all it will do is simply run the QState operation in the session, passing in the state to the state_in placeholder through the feed dictionary. We can now call this from our agent, passing in the session and then the state, but as a single batch size list to match the placeholder dimensions. Then from our Q values, we can select the action with the highest Q value with NumPy's argmax function. So now when the agent selects an action in the environment and receives a reward and next state, we need a function for it to calculate the target Q value and train the network. So we'll create a function train which takes in the current time step state, action, next state, reward, and whether the episode was terminated. So to calculate the target value, we first need the Q values of the next state to take the maximum value of. So we call the same getQState function from our neural network, passing in the session and the next state. We just have to make an adjustment for the case where there is no next state after a terminal state, so we can just multiply the Q values by 1 minus done to set all the next state Q values to zeros if done is true. So then we can calculate our Q target as the reward plus the discount rate gamma, which is usually 0.9 something, then multiplied by the max Q value of the next state. Okay, so now we have our state, action, and Q target values for training the network in the TensorFlow session. So we will make a function update model that takes in the session and the state, action, and Q target, and then run the optimizer passing in the state, action, and Q target into their placeholders in the feed dictionary. We can then call this function to train the Q network with the state, action, and calculated Q target. Then during training, we will call our agent's train function after each step in the environment. That gives us our next state, reward, and done, and pass those in after the state and the action. Okay, now we're ready to run this, but when we do, we see that our agent is just selecting the same action sequence in every episode and not training. The issue here is that when we call our getAction function, we are always picking the greedy action with the highest value, but initially our Q network will be set to random values, so picking the action with the highest Q values won't be the true optimal action. So if the agent always selects the greedy action and receives the same positive reward and next state, then the model will just reinforce that choice in that state and won't explore any other actions. This would mean that the agent could get stuck with an initial suboptimal policy for selecting actions and never discover potentially higher rewards from taking other actions. To fix this problem, we tell our agent to initially explore the environment by selecting actions randomly earlier in training, and then gradually selecting the actions greedily more often as the Q network moves closer to the true estimate. We can do this with a parameter called epsilon, or eps, which is the probability of selecting an action randomly over the greedy choice, and this will start as 1 for always randomly exploring at the start. Then, after we define our greedy action, we will save a random action as the randomly selected index from the range of action indices. Then we can select one of these actions depending on whether a randomly generated number between 0 and 1 is less than epsilon, and if it is, we select the random choice, otherwise we select the greedy choice. Finally, we need to decrease epsilon after each episode as our network improves, and we can do this by multiplying it with the decay constant in the train function if we reach a terminal state in the episode. We should also keep a minimum value for epsilon in case our training needs more exploration. So now when we run this, the agent takes a variety of actions and starts to increase its total reward after more episodes. But although our agent can get the maximum reward of 200 after about 400 episodes, the performance is still quite unstable. And taking 400 episodes is also quite a long time for training the CartPole environment. So let's try enhancing our training efficiency with a technique called experience replay. If this concept is new to you, I also have a video explaining how it works. So we'll start by creating a new class for the replay buffer, which takes in the maximum length of the buffer, where we will use the standard DQ collection as the rolling buffer of experience tuples. Then in our function to add an experience tuple, we simply append it to the buffer. Then to sample a batch of experience tuples, we'll take in a batch size and save a sample size variable to the minimum of the length of the buffer or the batch size in case we have less experience than the batch size. Then we get our list of samples randomly from the buffer, where k is the number of samples that we want. Finally, we want to separate the experience tuples into individual lists of states, actions, next states, and so on. So we unpack the tuples into the zip function and then convert each sequence to a list, which we just return as a tuple of lists. So then to use our replay buffer in our agent, we can create an instance in the constructor. Then in our train function, we need to add each new experience tuple to the replay buffer. We then get our lists of each experience type by sampling from the buffer. And now we just have to adjust our variable names in the Q target calculation to use the batched experience. So for retrieving the Q values of the next states, we pass in just the next states, which is already a list, so we don't need to wrap it in a list. Then we can use our done's list to index the next state Q values, setting all corresponding terminal state indices to a 0 vector. Then our Q targets are calculated from the list of rewards and the list of Q values for the next states, taking the max over the columns axis. Finally, we pass the list of states, actions, and Q targets to the update model function. And now when we run this, we see much faster training to reach the maximum reward continuously within a couple of hundred episodes. Well, you just learned how to code up your own deep Q-learning agent to solve the CartPole environment from OpenAI Gym. You could even try adapting that agent to solve some of the other environments in OpenAI Gym, which I'll eventually be doing in some of my later videos. Anyways, thanks so much for watching this video. If you found it helpful, be sure to give it a like and subscribe. And until next time, keep learning like a machine. Bye!